In this video, I'm going to walk you through the steps to testing the null hypothesis of equal means for the Weatherall et al. Study that looked at anxiety levels and whether anxiety levels would stay the same for a group of patients who underwent cognitive behavioral therapy. And so we have pre-treatment data, post-treatment data, and follow-up. The steps here for you to follow when it comes to doing a repeated measures one-way ANOVA. The steps are very similar to the one-way between subjects ANOVA. So the first step is check that the dependent variable is measured on a continuous scale. And in this case, the dependent variable was measured on a ratio scale because it was the percentage of time that people spent feeling anxious over the period of a month, I think, or something like that. So it can range from 0 all the way to 100 in theory. We can see someone scored as high as 92 pre-treatment. Okay, so we've got continuous data, so that's a check mark for that one, because the repeated measures ANOVA will work fine in that case. So the next one is the number of levels. In this case, we have 3 levels associated with the within subjects factor, pre-treatment, post-treatment, and follow-up. And that implies that I'll be able to do a protected Fisher's LSD as a multiple comparison procedure if I see a significant ANOVA first. And that would be my preference here because I only have 3 levels. If I had more than 3 levels, I wouldn't be able to do the protected Fisher's LSD. So let's give a check mark for that one. Next, check normality outliers across levels. Well, we can use the same procedure we use for the one-way between subjects ANOVA, descriptives, explore, and put the 3 levels in the dependent list, click on statistics, click on outliers, and click on plots, deselect stem and leaf, select histogram, and click OK. And just like the between subjects ANOVA, I'd be looking for skew to be less than 2 and kurtosis to be less than 9. I point out here that the sample size is 18, and that's true across all levels. So it's not that there are 18 people that did the assessment, 18 different people, it was the same people. So the overall sample size is 18. And we have here the mean, the standard deviation. So a mean of 44, so 44.9% was the average amount of time spent feeling anxious as reported by the participants in the study. Standard deviation of 20, that's a pretty big standard deviation. Skew of 0.6, so ebbing a little bit on positive skew, and kurtosis of 1.37, but not a problem. And then we have the mean of 25, so numerically it's dropped from 44.9 to 25.3. Skewness and kurtosis lower than 2.0 and 9.0. And then again for follow-up, the mean is 24.8 in terms of the amount of time spent feeling anxious. And skewness and kurtosis again are less than 2 and 9 respectively in absolute terms. So I feel fairly confident the data are sufficiently normally distributed for this analysis because it's nowhere getting close, not 1.5-ish. It's much less than that even. So I'd feel confident on that level. So the next question is, are there any outliers? And let's look at that through this histogram. Looks pretty good. It doesn't look like there are any obvious outliers there. And the actual interquartile range rule, however, is suggesting that there might be outliers in these data. And we can see that 2 participants got an asterisk, which based on the interquartile range rule with this is based on the 3.0 multiplier, is suggesting they're outliers. Here are 2 cases that they're warning signals, and this person here is a warning signal on the lower side. Now, this might be something where you would feel like you had to do something about it, such as Winsorize the data. I discuss Winsorizing in the one-way between subjects ANOVA chapter, and I talk about it in one of the earlier chapters relevant to descriptive statistics and such. I personally wouldn't Winsorize here if I wasn't forced to by somebody, like a reviewer. I feel like when I look at this distribution, I feel like it's not an entirely normal distribution, both in terms of skew and kurtosis. And to me, like the kurtosis is 1.3. To me, the outlier labeling rule is not quite working here. And technically, the rule works when the data are normally distributed, perfectly so. And as you deviate from a normal distribution, it increasingly becomes less reliable or valid as a test, I should say. When the distribution is positively skewed, I feel like I can be a little bit more liberal about outliers being on that side. So I'm actually not going to do Winsorizing here. I'm positive these values are legit values. They're within 0 to 100, so they're definitely possible values. And I feel like there's enough of a tail of a distribution that these values are not out on their own. So this is an example of, if you want to follow the rule tightly, do so. You can Winsorize these values to the next lowest point. And so that would be 67 or 68. So you'd have to reduce 92 down to 67 or 68, and you'd have to reduce 81 down to 67, 68. To me, that's a pretty big call to make on these data, where when I look at the distribution here, it doesn't look that bad. And the skewness is also not that bad. If skew was elevated and I had outliers as demarcated by the outlier labeling rule, I'd deal with them then. But in this case, I'm not. I feel like the results should be fairly trustworthy. Here's a distribution that's also positively skewed, but no outliers in post-treatment were identified. I'd also be a bit dubious because the distribution is so far from normal here about the outlier labeling rule. And in this case, again, here's a warning sign. Overall, it's a bit messy, definitely have to admit that. But I'm going to go ahead with it because the skew levels are not even close to 2.0. So even though outliers were identified, I don't feel like I should have to deal with them. If skew was elevated to 2.0, then I'd feel like I should have to deal with them. So the next thing is I need to check sphericity. And that's a new assumption. It's kind of like homogeneity of variance, if you will, in the context of repeated measures ANOVA. A little bit different, though, because it's homogeneity of the standard error, the difference between means is more appropriate to call it. So I'm going to make sure to check that. And even if it's violated, it's really simple to deal with it. I can look at the Hunfeld adjusted result. Is a very good balanced approach to dealing with violations of sphericity. And then I'm going to conduct the ANOVA. It's all done as one package. So let's go into Analyze and General Linear Model, repeated measures. So this is different. And we're going to have 3 levels associated with the factor. There's only one factor, which is time, basically, pre-treatment, post-treatment follow-up. You can give it a name if you wanted to. We can call it time. And change that. So time equals 3. And now I'm going to put these 3 variables in there. And I'm going to click on Options. And I want descriptives, effect size. You don't have to click on homogeneity test because that's only if there was a between subjects factor. But I do need to click on time, and I want to compare main effects and LSD, and it's saying it's not going to make any adjustment because that's appropriate because we're doing the protected Fisher's LSD. We need to see a significant ANOVA first before we can look at the LSD results. And we're going to plot the means because that's a nice way to look at things. We'll click Add, and we'll click Continue. And that should be all we need. We did click effect size, yep, so that's good. We've got everything we need. So here's the result. Here are the 3 levels associated with the analysis. And we got 44.94 as the mean for time 1, 25.3, and 24.8. So there's a drop, numerical. You can ignore the multivariate test table. Mauchly's test of sphericity, it has not been violated. P equal 0.292. If this were lower than 0.05, then we would have violated the assumption of sphericity, and then we would have had to use the Hunfeld adjustment here. But we don't have to. We can just go at sphericity assumed, and we get an F value of 14.59, P less than 0.001. So it's definitely rejected the null hypothesis of equal means. The means are not equal. Well, I say definitely, with a certain level of probability, very low level, that we make a mistake. And here's partial eta squared, 0.462. So 46.2% of the variance in anxiety levels is accounted for by what time period people's anxiety was measured across receiving CBT. So that's quite a whopping eta squared. Now that also takes into account the correlations across levels, which I'll look at right now. Let's actually look at the correlations. And they should be positive. And in fact, here are the correlations across levels. And we have positive correlations, which implies that people who were more anxious at pre-treatment tended to report themselves to be more anxious at post-treatment and at follow-up. So it's a general anxiety factor that you will see very consistently across repeated measures data. In fact, that's the power of the within subjects design, is that you do have those positive correlations. And so we can say that 46.2% of the variance in anxiety was accounted for by time, pre-treatment, post-treatment follow-up, controlling, for the correlations across the levels for anxiety. So this, again, is the power of the within subjects design. Now, SPSS automatically reports tests of linear and quadratic effects. And SPSS is telling me is that there's a linear effect in the means, and there's also a quadratic effect. Now, when there is a quadratic effect, I would probably only interpret the higher order term. So I wouldn't say that there's a linear effect here. I would say that there's actually a quadratic effect because there's one bend in the means. But these researchers weren't that interested in this sort of thing. So I'm only pointing this out briefly, that there is a quadratic effect. You can essentially ignore the between subjects effect in a one-way repeated measures ANOVA, not typically interesting at all. And so we've rejected the null hypothesis. The omnibus null hypothesis has been rejected, but we don't know which means were actually different from each other. We just know that one comparison at least was significantly different. And here we have the pairwise LSD differences. So it's saying adjustment for multiple comparisons, least significant difference, saying there's no adjustment here. Fine, that's okay, because we're doing a protected Fisher's LSD. And here we have a statistically significant difference between time 1 and time 2. And you actually have to look, you have to remember what that is. And that's pre-treatment versus post-treatment. Because SPSS does not label it so that you know what you're actually comparing. It's just literally going 1, 2, 3. So this is pre-treatment versus post-treatment, and that's statistically significant. So there was a statistically significant drop in anxiety from pre-treatment to post-treatment. So that's support for the idea that cognitive behavioral therapy helps people feel better with their anxiety. Now, what about the difference between pre-treatment and post-treatment? That was also statistically significant. P is less than 0.05. In fact, it's 0.001. So the difference between pre-treatment here and follow-up was statistically significant. So people's anxiety levels stay down after they receive treatment. So they're no longer receiving treatment, but their anxiety levels are still low, or lower than they were pre-treatment. Now, finally, the difference between post-treatment and follow-up. So between 2 and 3, post-treatment and follow-up was not statistically significant. It's a very small difference of 0.5. So 25.33 versus 24.83, a p-value of 0.904, definitely not statistically significant. No, not even close to 0.05. And you can see that there's nothing going on here. So the researchers would have been happy to see a drop in anxiety, and it's statistically significant, which suggests that CBT works at helping people feel better about anxiety, reduce their anxiety levels. And at follow-up, it stayed lower. It didn't go back up, and it didn't go down. There's just evidence that we didn't reject the null hypothesis of any difference. So that is a one-way repeated measures ANOVA, going through all the steps. I did the effect size with the partial eta squared, and I've got a graph, which is a line graph, which is an appropriate graph for this type of analysis because it's within subjects in nature. Now, the last thing I'll say is that you should be calculating Cohen's d for each Fisher's LSD that you conduct and report. So that's the end of this analysis, doing a one-way repeated measures ANOVA.